a substitution, we held the level of happiness constant. We stayed on the same indifference curve. And then we looked at how many Reeses are you willing to give up for one more Hershey's. Here, what we're going to do is instead of holding utility constant, we're going to hold output constant. And we're going to see how many units of capital can you give up if you hire one more unit of labor and holding your level of output constant. Very similar concept. So let's do this graphically, which I think is the easiest way of getting at this issue. OK, so draw an indifference curve. Right? Before we draw indifference curves, we're always labeling our axes nicely. So I've drawn one here, and I've picked these points because it makes it nice and easy to draw these. 10, 2, 7, 3, 5, 4, 4, 5. And then here we go, and here we go. So I'm going to draw my isoquant. Wow, this looks almost like a real smooth isoquant. One little miss here, but with a little big dot, we're good. So I'm getting better at this thing. By the way, I've read this really neat study that while you're studying and you get something right, don't give yourself gummy bears as rewards. What you should be doing is pat yourself on the shoulder and say, good job, Max. Rewarding yourself by acknowledging your successes apparently does things to your self-esteem, and you then perform better on next tasks. So do it quietly if you're studying in the library, because other people will think you're weird. So the marginal rate of technical substitution decreases as L increases. So what am I saying here? Right? This is my isoquant. Let's say this is output level 10 units. So if I move from one point to the next, right, let's start here and move here. So point A to point B. So what am I doing by moving from point A? I'm going from 10 units of capital, 2 units of labor, to 7 units of capital, 3 units of labor. All right? So what am I doing? I'm increasing labor by 1 unit, and I am decreasing capital by 3 units. Right? So my change in capital is -3. My change in labor is +1. I'm producing the same amount of output. Right? So by going from A to B, I'm still producing 10 units. I'm giving up 3 units of capital, and I'm purchasing 1 more unit of labor, but I'm producing the same amount of output. So the marginal rate of technical substitution is the change in K over the change in L, which here is going to be rise -3 over run +1. It's going to be -3. Let's do this again. Let's move to point C. Point C, I'm giving up 2 units of capital, and I'm buying 1 more unit of labor. So my change in K is -2. My change in L is +1. So in my move from B to C, my marginal rate of technical substitution is change in K over change in L is -2 over +1 is -2. So much like for imperfect substitutes, right? My marginal rate of technical substitution as I wander along my indifference curve was dropping. Right? Here, the same thing. As I wander along the isoquant, my marginal rate of technical substitution starts dropping. All right? Let's do one more, just because it's so much fun. Yay! Here, change in capital, -1. Change in labor, +1. So here, my marginal rate of technical substitution is change in capital over the change in labor is -1 over +1 is -1. You could keep on going. If you go to point E, it'll be -0.5. And if you go to the last point out here, F, it'll be -1/3. So the marginal rate of technical substitution in absolute value starts diminishing as you wander along the isoquant. Now, for the indifference curve, we showed that that was true. Right? The marginal rate of substitution changes as we wander along an imperfect substitutes indifference curve. And then we related this to what? I want somebody new who doesn't usually speak. Somebody else here named Max. Anybody's named Max? No. How about Adam? Picking random names. Is there Noah in the room? All right. Random volunteers. Otherwise, I'm going to start pointing. All right. You're it. So why did the marginal rate of substitution start diminishing as we wandered along an indifference curve? You're 90% correct. All right, good job. It's because the ratio of marginal utilities started changing. Right? So as you wander along an indifference curve, your stash of Reese's gets smaller, so the marginal utility of an additional Reese's rises, and your stash of Hershey's gets bigger, so the marginal utility of Hershey's falls. So the marginal rate of substitution we showed is just the ratio of marginal utilities of the two goods. So as you wander along the indifference curve, that ratio becomes smaller in absolute value. So that was cool. Is there an equivalent concept here for this amazing isoquant? Well, of course there is. Max, the picture looks the same, right? In fact, if you go back to your indifference curve, it's the exact same picture, all right? The exact same picture, only it's a marginal rate of substitution instead of marginal rate of technical substitution. Even the numbers are the same. If you go back, you can also see how much better I'm getting at drawing on this thing, because that really didn't look very good. Okay. See? That was it. See? You're doing a good job, Max. I'm already feeling better about myself. So can we show this mathematically, and can we relate the marginal rate of technical substitution to marginal utility? Well, of course we can't relate the marginal rate of technical substitution to utility. Those are two totally different corners. One's a consumer issue, the other one's a producer issue. But what I'm going to be able to do is I'm going to be able to relate the marginal rate of technical substitution to the marginal product of labor and the marginal product of capital. Meaning my ability to substitute between capital and labor is going to depend on how productive the next unit of capital is relative to the next unit of labor employed. So let's show this. Let's do a proof. It looks exactly the same like that last proof we did, and see if we can somehow relate marginal rate of technical substitution to these marginal products. So start at the end, right? Marginal product of labor we defined as the change in output due to the change in labor, right? How much more output do you get if you hire delta units of additional labor? The marginal product of capital is the same thing, only it's how much more output do you get if you hire delta units of additional capital. So this is just the definition of the marginal product of labor on the left and the definition of the marginal product of capital on the right. Now I'm going to do some math magic, okay? I'm going to bring delta L over here, and I'm going to bring delta K over here by multiplying the left equation times by delta L and the right equation by delta K. So what you've got here now is MPL times delta L equals delta Q. On this one here, you've got MPK times delta K, this is not a minus, times delta K, that's equal to delta Q. Well, Max, that doesn't really tell me anything. In fact, this looks horrifying, and your delta, if I may note, looks like an A. That's a delta, and this here is an L. So what do I know is true about quantity on a given isoquant? Does it change? Does output change on a given isoquant? No, because iso means same, right? So it doesn't change. So on a given isoquant, what's the value of delta Q? 0, right? So if I'm on a given isoquant, which I am here, and the marginal rate of technical substitution is defined for a specific isoquant, this here is 0. So I've got an equation on the left that's equal to 0. I've got an equation on the right that's equal to 0. Two things that are equal to 0 are equal to the same thing, right? So here we go. I don't know, how does it go? Two things that are equal to the same thing are equal to each other. There we go. Come on. Can you tell I went to bed at 3? No, Max, you make just as little sense as you do on a regular day. Points taken. Okay, so set those two equal to each other. Now, Max, that still doesn't tell me anything. So what I'm going to do is I'm going to divide this equation by MPK and also divide it by delta L. So what I'm going to do is I'm going to bring this thing over here and this thing over there. So what that gets me is delta K over delta L is equal to MPL over MPK. Now, for $1, what's that? Say it loud. Oh, I don't have that many dollars. Who wants $1? You. There you go. That's the marginal rate of technical substitution, right? There you go. You're welcome. So that's the marginal rate of technical substitution. So what I've done here is I've simply shown that the marginal rate of technical substitution, which we defined as the change in capital over the change in labor on a given isoquant, is simply proportional to the rate, the ratio of marginal products, right? So what we said for marginal utility, right? Think of this as an indifference curve for a second, right? As we wander to the right here, your stash of at the time Hershey's got bigger, so the marginal utility of Hershey's gets smaller. As you move to the right here, your stash of Reese's gets smaller, so the marginal utility of Reese's gets bigger. So the marginal rate of substitution for the consumer was the marginal utility of Hershey's over the marginal utility of Reese's, right? And that marginal utility of Hershey's becomes smaller as your stash gets bigger, and in the denominator, the marginal utility of Reese's gets bigger as your stash of Reese's gets smaller. So what happens here now, right? We had diminishing marginal utility. The more you get of one good holding everything else constant, the less additional utility you get out of it from additional consumption. Did we have something similar for the marginal product? The law of eventually diminishing marginal product, right? So same thing goes here. So as we go down here, move towards the right on our isoquant, what happens? I'm using more labor. What happens to my marginal product of labor out there? So you're using more of it, right? It becomes smaller. What happens? Are you using less capital over here as you move along? Yes, you are. So your stack, the amount of capital you're using is smaller, so the marginal product of capital goes up. So the marginal rate of technical substitution here is the marginal product of labor, where as you move towards the bottom right, you're using more labor, this goes down, and you're using less capital, the marginal product of capital goes up. Right? So that ratio becomes smaller in absolute value, and that's behind what happens to the marginal rate of technical substitution. Right? It diminishes, and it's simply due to the fact that marginal product eventually diminishes as you use more of one input holding the other one constant. I think that's pretty intuitive and a nice parallel to what we showed in consumer theory. All right. So, Max, I've heard about something called returns to scale. It's a cool word. At the Thanksgiving dinner table or whatever holiday is your favorite holiday that family comes together and then starts yelling at each other after the second glass of wine? No, that only happens in the movies. But the point here is you sit there and throwing around words like returns to scale really makes you sound college educated. The problem with returns to scale is I think about 50% of the time that people use it, they have no idea what they're actually talking about. All right? Returns to scale, economies of scope, economies of scale, diminishing marginal returns, this all turns into one sort of foggy set of concepts that can be used interchangeably. That is clearly not true. Right? They're all very distinctly different. So let's talk about what returns to scale actually are. Returns to scale, if you have multiple inputs to your production process, like most production processes actually are, have a very simple definition. That means how does output change if all inputs are increased by equal proportions? So if you increase all of your outputs by the same proportion, meaning you increase labor by 10% and capital by 10%, I like to think about it in terms of doubling. 100% increase, it's just easier to think of it that way. So how does output change if you double all inputs, right? So returns to scale come in 3 flavors. They come in decreasing returns to scale, constant returns to scale, and increasing returns to scale. Easy to remember. So constant returns to scale are production processes where if you double all inputs, you double all outputs. This is the potato salad production function. So, you know, everybody, I'm from northern Bavaria, where making potato salad is it's a thing, right? So they're secret family recipes. They go back to like 1322. But let's think of a simple potato salad, mayonnaise and boiled potatoes, all right? But this is what constant returns to scale are. I double the amount of mayonnaise, I double the amount of potatoes, I get twice the potato salad, right? Constant returns to scale. Double all inputs, get double the outputs. Decreasing returns to scale means if you double all inputs, you less than double all outputs, right? This is actually a lot of production processes here where even if you double capital and you double the amount of labor, you less than double output. Right? We'll have some examples of that later on, but it's a really simple concept in the sense that, you know, if you hired 5 workers before and you had 1 machine, now all of a sudden you hire 10 workers and you have 2 machines, you were hoping to double output, but what actually happened is you went from 5 units produced to 8 units produced, but you're hiring twice as many inputs, having twice the input cost, but not double the revenue. Increasing returns to scale, bless you, as we'll see, are processes where if you double all inputs, you actually more than double output. Double the amount of capital, double the amount of labor, you more than double the amount of output. The examples I will pull out when we actually start talking about what this means for costs here, but an argument could be made for firms that have significant fixed cost investments. We often describe those as increasing returns to scale firms here, which is going to mean in the long run that average costs and marginal costs are going to be dropping everywhere. But that's beyond where we are now. For now, it just means double inputs, more than double output. We can also have something called varying returns to scale. Let me show you these graphically, each in turn, and then we're going to move on to costs. So just to impress on you how important labels are, what I'm going to do is I'm going to draw a constant returns to scale production function. Okay? The easiest way to do this, start at 2, 2, go to 4, 4, go to 8, 8, and then draw some, Draw some isoquants through these points. That's not a nice one. Ah. Let's try again. Come on. There we go. Can I tell returns to scale from these pathetic isoquants that I drew? No, right? What do you need? You need labels. Why are these constant return isoquants? Well, I double inputs. Okay, I go from 2, 2 to 4, 4. At 2, 2, I'm producing 10 units. At 4, 4, I'm producing 20 units. I'm doubling inputs. I'm doubling output. Again, if I double inputs again, I go from 8, 8. From 4, 4 to 8, 8. And I double inputs. And again, I double outputs. I go from 20 to 40. Now, Max, that's kind of boring. Let's do increasing returns to scale. I bet you these isoquants look amazing. Question. Exactly. So that's exactly it, right? So returns to scale, you just see it in the label. So the way to set it up is pick 3 points where each time you double inputs, right? Again here, pick 2, 2, 4, 4, and 8, 8. Each time I double inputs. Draw some arbitrary isoquants that don't violate any of the laws we've agreed to. Here again, an isoquant. These look just as pathetic as the last ones, right? In fact, they're very close to the last ones. The only way they differ is by their labels. So here, I go from using 2 units of each input to 4 units of each input. I double inputs. This is increasing returns to scale. I more than double output. So I don't know exactly how much this has to be, but it has to be more than twice what I did at 2, 2. Then if again, I double both inputs, I go from 4, 4 to 8, 8. I have to more than double output, right? I double from 4, 4 to 8, 8. I go from 25 to something more than 50. Could be 60, 70, 80, whatever you want it to be, but it just has to be more than doubling. If you wanted to draw the same thing for decreasing returns to scale, so if you wanted to do decreasing returns to scale, the label here would be somewhere between 10 and 20. So 15 maybe. And if this is 15 and you double again, it has to be somewhere between 15 and 30, so 25. So the key to drawing these pictures is pick combinations of inputs, 3 of them, where each time you double inputs, and then draw isoquants through it, and then make sure you label them correctly in the sense that they go with the concept that I've asked you to draw here. Okay. Does a production function always have one type of returns to scale? Is it either constant, decreasing, or increasing returns to scale? And the answer is no, right? There are some production processes which at low levels of output have decreasing returns to scale, then a little bit of constant returns to scale, then a little bit of increasing returns to scale, or the other way around. At low levels of output, you have increasing returns to scale, you go to constant, and then decreasing returns to scale. So how do you show that? In order to do that, what you actually need is you need 4 points. You go from 1, 1 to 2, 2 to 4, 4 to 8, 8. Okay? And again, here's one isoquant. Here's another one. These are all decreasing everywhere. If they look like they aren't, you're not seeing right. I'm joking. They look a little bit bumpy when they shouldn't. But again, I go from 1, 1 to 2, 2 to 4, 4 to 8, 8. So 3 sequential doublings of input. So let me draw you the following set of labels here. Q is 10, Q is 25, Q is 50, Q is 78. Okay, here I go from 1, 1 to 2, 2. I double inputs. I go from 10 to 25. I more than double output. So here I have an area that is increasing returns to scale. Then I go from 2, 2 to 4, 4. I again double inputs, and I exactly double output. So I go from 25 to 50. So this is constant returns to scale. And then I double again from 4, 4 to 8, 8, and I less than double output. I go from 50 to 78. That's decreasing returns to scale. Right, so this is a production function that has increasing, constant, and decreasing portions of its surface that that has portions of its surface that are increasing, constant, and decreasing returns to scale. So each production function doesn't just have to be constant, decreasing, or increasing. It can be a mix. Okay. We live in an area where an area and time where technological progress reigns supreme. Okay. WhatsApp, that I didn't even know existed, allows people to connect with each other, and that technological innovation of being able to send pictures of your cats to your best friend is worth, in net present discounted profits, $19 billion. All right, that's technological change. I'm not trying to make fun of WhatsApp. It's apparently amazing. I'm just behind the times. So technological progress really matters. We're really trying to figure out how to more efficiently use our resources or come up with better ways of doing business. So let me think of a business that I know well. So I have a good friend who's in a very high-tech business. He prints T-shirts. All right, so he had a silk screen thing, so I don't know if any of you know what a GoCo press is. It's essentially a glorified version of a GoCo press where you make a silk screen, you project an image, and you put a screen on a T-shirt, and you squeegee across, and then it paints funny jokes on T-shirts that you guys then buy on Telegraph, right? So what he had is he had a unit of capital, which was his squeegee silk screening setup, plus his labor, right? At that point, he made, let's say, 10 units of T-shirts